Uh, so here is the spread footing that we're trying to design, strip footing. And just before the break, I was trying to show you where is the critical section for shear. Okay. Then if we proceed, when in shear design, what are we trying to do? We're trying to make sure that the VR or the shear capacity of your one-way slab exceeds the actual factored force affecting this slab. And what is VR or how much is VR? In general, VR, which will be the shear capacity, it comes from two components. It comes from concrete and it comes from stirrups. In beams, we use stirrups. In slabs, what do we do? Do we still use stirrups?
No.
No stirrups.
No, we don't. So that's why, and as I said, the strip footing is just a one-way slab, and that's why I already canceled the VS. So really, what we have to do is we need to make sure that VR is more than VF, and how much is my VR? It is only VC. Okay. Now, how about bending? Please look at this picture. It is a very nice picture to show you how this strip footing acts under the acting load. So we have a load coming from the wall down, and the soil will react by a reaction going up, and simply your footing will bend this way. As I said, it will be a one-way cantilevers out from to the left and the right from the wall. And simply, if you know that, so what you have to do is, based on this, you have to decide where is the critical section and what is the moment at the critical section. So I showed here the critical section at the face of the wall, at the face of the wall, and I have more discussion coming on the next slide. But once you say the critical section is section 1-1 at the face of the wall, together we will simply estimate the moment. And once we know the moment, we will go ahead and find what should be the area of the steel needed to resist this moment. Now, a little bit of more discussion about the critical section. So the critical section, not really one location. It depends on this footing, what rests on the footing. Sometimes it's concrete, and we simply combine or connected the concrete wall to the footing by a means of dowels, as we will see. And so in this case, that critical section will be at the face of the wall. If you if you're adding a wall, but it's not concrete, it is a masonry wall. And so if it's masonry wall, then the section will be 1/4 of the thickness of the wall in from the face of the wall. Okay. Really, it depends on the connection between the wall and the footing. If the connection is concrete and to concrete, and you have some dowels coming through, then critical section will be at the face of the wall. Masonry, we cannot get this kind of good connection. So what we do is we go in 1/4 of the thickness of the wall. If you add a steel element, which is not really common, we add columns. If you add a column that has a base plate, in this case, the critical section will be 1/2 of the cantilever of the face of the base plate. Anyway, let's make it clear for you and make it simple. You can see here I mark it in red, which means this will be our case. We're resting a concrete wall on top of a concrete strip footing. So where is my critical section? Will always be at the face of the wall. Now, it is time to see what happened next. Once you are able to find the moment, then what you do is we will use the flexure design theory that you learn in my class to find what is the area of the steel. And remember, as I said, this is a one-way slab, and the load, it has only one direction. So this will be the direction of the load. So the load will get to this direction. So if you remember, in one-way slab, there is one direction called the main, another direction called the transverse. In one-way slab, there were two directions. One, we call it main, which 100% of the load will go into this direction. And the perpendicular to this direction called the transverse, And if you remember, we add reinforcement in both directions. We add reinforcement on the main direction and on the transverse. The difference is the main direction reinforcement, it comes from the moment, from the load. For the transverse, there is no load, and what we do is we just go ahead and add the minimum reinforcement in the transverse direction, if you guys remember. So, I mean, let's make it clear, okay? Let's make it clear. On this picture here, I have a question for you, and actually cannot be a question because the answer is already on my slide. So remember, look at there. So there are two kinds of reinforcement. This reinforcement that goes parallel to the cantilever, and there is reinforcement that goes perpendicular to the section here, okay? Which one is the mean and which one is the transverse? Probably I need to zoom in. So you can see on this picture here, there are two, it's a mat, huh? Like some rebar goes perpendicular to the wall and the other one goes parallel to the wall. Which one you think will be the mean and which one will be the transverse? The answer is on my slide here. The one that goes with the cantilever direction is the main reinforcement, the main reinforcement. And the one is simply perpendicular to the cantilever. This is the transverse reinforcement. And remember, everything I taught you before for one-way slab, every single clause, every single condition still applies. If you remember, for example, we talked about the spacing between the rebar on the main direction. Can we go any spacing? Can we space our rebar 600 mil, 700 mil, 800 mil, 1 meter? No, we can't. It is actually, you have to find the minimum of two numbers, which is 3 times the thickness of the slab or the footing, or 500 mil. You take the minimum of those two numbers, and this will be the maximum spacing. Okay, why do we add transverse reinforcement? Still the same reason, because of the integrity. Yes, we deal with them as adjacent 1 meters, but at the end of the day, it's a plate action, so we need to add transverse reinforcement, and also for temperature and for shrinkage. And we add here a minimum reinforcement in the transverse. For the transverse, do we go with the same spacing as the main? No, the code has a different number, so you have to estimate 5 times the thickness of the slab, or 500 millimeter, and this will be the maximum spacing between the rebar. So you can tell from this slide here that all the conditions and code requirement that applies for one-way slab still applies for strip footing, because it's nothing more than a one-way slab. Now here is our first example, okay? Our first example is we need to design a strip footing with the following information. We need to design a strip footing with the following information. Let's go one by one. So for the thickness of the wall, and remember, thickness of the wall is not the thickness of the footing. That's the wall sitting on top of the footing. It's a 200 mil, it's an 8-inch, just like any like foundation, like a basement wall, 8-inch concrete wall. The load that comes from the building to the footing is given here. It is dead load is 60. And remember, it's per meter. It is per meter. So the load is estimated per meter. And the live load is also 60 kilonewton per meter. As I said, for loads, for walls, all the loads are expressed in kilonewton per meter, per linear meter. Now, my geotechnical engineer gave me the Q allowable. Okay, please watch this, very important. Okay, so my geotechnical report did not provide Q factor, it provides Q allowable, okay, which is 100 kBA, 100 kBA. Also, we are going to use a 15M reinforcement. The aggregate size is 20 millimeters. The F prime C is 25 MPa. And I need to just remind you that this number here is based on strength, but sometimes when the soil has some sulfate, if the soil has some sulfate, then in this case, probably you need to bump up the 25 to some other values bigger for the durability issue. So be careful. In this example here, I use 25, and I just assume that there is no like sulfate in the soil. Now,
Tyler,
okay, go ahead.
if there's sulfate in the ground, why wouldn't we use like a different specialty concrete instead of upping the MPA?
We do the same. It's better the code when you have a sulfate S, like let's say high sulfate or medium sulfate or severe sulfate. The code not only asking, you have to do both. You have to use one kind of cement which is sulfate resistant, and also increase the F prime C. Both of them, not only one, sir.
Okay.
What about like admixes, like corrosion inhibitors?
Actually, the sulfate is not really an enemy with the steel. So the sulfate doesn't hurt the steel. The sulfate is not a friend with concrete. It reacts with concrete and simply makes some crack. The one that is enemy with the rebar is the chloride. Okay?
All right.
Okay, so now one thing which I need to make it clear. So the thickness of the footing is something that is not given. The thickness of the footing is not in general given. Okay, when I'm an engineer trying to design a building, I'm going to use my experience and simply assume a thickness of the footing, and if this thickness works, then I'm going to continue. If this thickness fails, then I will have to re-estimate again and increase my thickness and check it and so on and so forth. So please think about this process as a kind of a trial and error. So you pick one thickness, you check it. If it works, great. If it doesn't work, then we repeat the process again. For this exercise, I'm saving your life and I give you the thickness. And typically in the final exam, I will also give you the thickness of the footing, the thickness of the footing. So in this example here, I already gave you the thickness of the footing, which is 250 mil, which is 10-inch footing, 10-inch footing. And all we have to do is, you will see, I'm going to check this thickness and see if it works or no. Now, let me show you on how to solve this problem, which you will see very, very simple. The only tricky part is the start only. The tricky part is the start only. So because my geotechnical engineer provided Q allowable, so you can see here, this 100 kVA is a Q allowable and no Q factor. It means do not factor your load. So what you do is you go and you add 60 plus 60. So you say 120, and I made it clear, and that's not factored load. Just live plus dead without multiplying the load by any load factor. So now we know that my unfactored load is 120 and my soil can take 100. Now, what should be the size of my footing? Very, very simple. To find the size of the footing is going to be nothing more than you divide the load, you divide by the Q allowable, which is 120 divided by 100. So you will get 1.2 meter. Nice number, huh? It is 1.2 meters. In general, this number can be 1.25, 1.26. Do we have any rounding rule? So I came here with a rule for you is use 100 mil, and we always round up. Why is that? Why we don't round down? Any thoughts of why we don't round down?
Because then it gives us the wrong allowable strength.
Give us a higher than 100. So think about it this way. If my geotechnical engineer is saying maximum 100 and you went less than 1.2 and you re-estimate the Q, what happened is you will get more than 100, which is not allowable. It's more than allowable. Okay? So that's why when we pick the concrete dimension, sorry, the width of our footing, we simply have to round up. And the reason why we round up, because this Q allowable, it's the maximum allowable stress on the soil. Anyway, for this example here, I don't need to round up or down because my number is simply rounded already. There's 1.2 meter. Okay? Now, here is the next step. So from this point on, there is geotechnical discussion. So the geotechnical only be used to size the dimension of your column. Remember, this B here is simply the width of your footing, and I showed already on this 3D picture. Okay. Now, what you have to do next, which will look weird for you, I went back and I divide. I'm trying to find my QF, which is my factored soil bearing. I am here dividing the axial load, but it's factored already. So you can see I got the 60 times 1.25 and the 1.5 times 60, and then I'm dividing by whatever I chose for the width of the footing. Why I'm doing this? Because simply all the structural design, for example, check for shear, check for bending, finding how many bars, all of that we have to do that on the ultimate limit state. Yes, my geotechnical engineer give me Q allowable of 100, but when I design my rebar, I need to use an ultimate limit state, and that's why I'm doing factoring right now. Okay, I know that this is kind of hard to understand why at the one state I'm using B working without factoring, and then why later on I'm getting my Q factor, because all my concrete design will have to be in ultimate limit state where all the loads are factored. Okay, so you can see here the Q factor is 137.5. Now let me ask you, what happens if my geotechnical engineer provided me with a Q factor already, not Q allowable? Like he already converted and give me my Q factor. In this case, you will see in this step here, I have to factor my load. So if the Q factor is given, so this number has to be factored. So I have to multiply here times 1.25 and this number times 1.5. And then I divide my B factor, divide my Q factor, and I will get the size of my footing and to be rounded if needed. Okay?
So, Tahir,
Mhm.
if you're given so in this example we're given Q allowable, but if we're given Q factor to find B, we just use the factored number.
You do load combination and you take the maximum of the load combinations, then this will be your B factor, where you divide it by the Q factor to get the dimension of your column or size your footing.
Okay.
Okay, guys, no matter what is the Q given to you, when you try to design for shear or for bending, and I put the line here, so this line here, it's simply from this point on, we're designing same as we did for beams and for columns and for footing. So this one here is our structural design. This part here on top of the red line is geotechnical design. Okay, and you can see it's very little. We're only trying to size our footing in this step. Okay, as I said, no matter what you do here to find the thickness, the width of your footing, then for your design, it must be an ultimate limit state where all the loads must be factored. Okay, now let's move on. Now let me remind you, and you will be surprised that nothing new from this point on. Everything you learn in my class will be exactly the same without even a single change. Okay, so number one, when we design for shear, how we do that? I know that this was like a kind of a 2 weeks ago, and I'm not sure if you still remember that. So in order for us to design for shear, that's how we do it. We need to go ahead and find our D, and D is the D effective, okay, which is the 250 mil, which is the thickness of your footing, minus the cover, minus 15/2. Why 15/2? Because we're going to use a 15M. And then here is the thing that I want to bring your attention to. Please take a note. Look at this number. So what do you think? What about 75? What is 75?
That's a cover. Concrete
That's the cover.
Cover, yeah.
Okay, so I made it clear here. Concrete cover is 75 millimeter, as concrete is poured against soil. Okay, I think I said this probably on the first few classes, I said when we pour concrete against bare soil, then the concrete cover has to be 3 inches. Okay? Please, for our footing design, the cover will always be 75 millimeter. Please take a note. And then we found here the D, and then next what we do is we simply find the D sub V. Can anybody remind me what is the name of D sub V?
That is the depth, the effective depth of the shear.
Thank you so much, Jelly. Thank you, that's true. So the effective shear depth is simply the greater of two numbers, which is 90% of the D that we just got a minute ago, or 70% of the H. So you can see here, I did the math, and then finally, the D sub V is equal to 180 millimeter. Okay? Now, next is, let's try to find what is the VF. What is the shear force trying to shear the critical section? And I know you'll ask me, what's the critical section, okay? So I'll go back to here, I will remind you here. Guys, look at this, please. I'm gonna put some dimensions. So the dimensions are from this point to this point here is how much? Is a 1200 mil. Would you agree?
Yes.
Yes.
Okay, how about from here to there? It's about geometry. So please look up my sketch. Do you guys
That's
know what's this
200.
number? This is the
200.
200 mil. Okay, now how about this guy here? This dimension from here to there.
180.
That's your DV.
That's 180. So how much left of the cantilever? Not very difficult. So really what you have to do is we are trying to find the distance from here to there, which is very simple. It is 600, which is half of the footing, minus 100 mil, because that goes to the center line, minus 100 mil, minus 180, and so this will be a 600 minus 280, and so this will give you this cantilever. And if you multiply this part by the QF, what do we get? So it's over here, guys. We simply multiply the QF, which is 137.5, multiplied by half of the width of your footing minus 0.1, which is half of the wall thickness, minus 0.18, which is the DV. So what you get here is the VF, which is the force trying to shear this section. I'll come back and I'll show you. So all you have to do is you multiply the QF multiplied by this length, and you will get this, you will get the force trying to shear this critical section. Hopefully this is not very difficult. Then next, once you have the VF, then we want to make sure that my concrete has enough capacity, which means my VR, which is my VC, more than this 44 kilonewton. Now let's do it. So the VF is 46, and we're trying to find what is my VR, and in general VR is equal to VC plus VS. Since we have no stirrups in footing, then we cancel out the VS. How much is my VC? Nothing super, nothing new. It is phi C multiplied by lambda square root of F prime C beta dV times B. There are few notes here. Always, guys, the B, just like one-way slab, it is 1 meter always. And the dV, we already found this dV, it's 180 mil. The F prime C is 25 MPa. The lambda is 1. The phi sub C is 65%. So it looks like there is only one parameter, and which is beta. And I show you here how did I get the beta. If you read the code under 11.3.6.1, actually it's not 0.1, it is 0.2. So it's 11.3.6.2. You will find for a special member types, which is any slab less than 350 millimeter thick. And remember, our footing is 250 millimeter. 250 millimeter, which means less than 350. It means my beta is equal to 21% and theta is equal to 42 degrees. So very simple. All you have to do is just put all the numbers, and the surprise is we have 122.85. And what does it mean? It means my footing can take a shear of maximum 122.85 kilonewton, while in fact the force is trying to shear this footing is only 44, and it means what? It means it's okay. It means my concrete is strong enough. Okay? And so what happens if this is not happening? What happens if my VF exceeds the VC?
Then you have to change something, your F prime C.
Okay, so yeah, exactly. You have to change F prime C or change the thickness of your footing. Okay, change thickness of the footing. So that's another option. Okay. Now we can tell from this step here that the thickness that I gave to you, 250, is good. Then we can proceed. But please, 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 if the thickness is not enough, before you look at the bending design or the flexure design, please make sure you change the thickness, check it, and if it works, then you proceed to the bending. So please don't go to this step while the thickness of the thickness of your footing is not enough. Because some people, they do that. It fails in shear and they keep going. Don't do that. If it fails in shear, then please go back, change thickness of the footing, and then continue to until it passes this condition, and then proceed to the flexure design. Are you guys following?
Yes, sir.
Yep.
Okay, next is bending design, flexure design. As I said, very simple. The slab or the footing will bend this way. Please watch this. This is very nice picture. It tells you what's happening. As you push down, the soil will react and it will bend the footing this way. Cantilever from both sides. Where is the critical section? It's at the face of your wall. And what is the moment at the face of the wall? So what is the moment? Very difficult. It is QF, and it's not Q, it's QF. It is the soil reaction under factored load. Multiply by this cantilever length, and then multiplied one more time by the cantilever length over 2. So if I multiply QF by A, I get a point force here in the middle, and then the lever arm of this guy is A over 2. So here we go. The moment is equal to QF multiplied by A squared divided by A multiplied by B, while B is always
1 meter.
1 meter. 1 meter. So that's how we find the moment. Let's do it here. So the moment is 137.5, which is QF, multiplied by the cantilever length squared divided by 2. So we have 17.1 or 0.2 kilonewton meter. How can we find the rebar? Here is the surprise. Nothing new. What you have to do is you go ahead here and then you use the MF divided by BD squared, which is 1,000 always. This is 1,000 always because it's a 1 meter wide strip. And this number is the D that I got before, and D squared. So we got here our K, and K is equal to 0.613 MPa. Next is you go to the table. Do you guys remember this table, or you forgot by now?
Yes, we do.
The table or table 2-21, which you already have it on the slide. And you have it, I give it already as the whole table. I give it to you. Okay. So on this table, you go on the column that has a 25, and you go with the K equal to 0.613, and you will find the row, the reinforcement ratio in the table, which happens to be 21%. If you find the reinforcement ratio 0.21%, this is how you find the area of steel. So 0.21, and please don't forget it's a percentage, which means you have to divide here by 100. Then multiply by the G, multiply by the B. So we have here 351 millimeter square. We need to make sure that this exceeds the minimum area of the steel, So what we do here is we simply go ahead and multiply 2 per 1,000, multiply by area gross, which is 2 over 1,000 times 1,000. And remember, this area gross, not B times D. This is B times H. So 1,000 times 250. And then finally, it means 500 millimeter square. And please don't bother with this, Don't bother so much with this. So it's a 500 millimeter square. And what does it mean? It means the moment needs a 351 millimeter square of steel, while the code says the minimum you can add is 500. What can we do?
Now increase.
Nothing.
You have to
Within.
reduce your D, your H.
No, you have to use the minimum. Why should I change my H? Yes, you can
Okay,
do that.
yeah.
You can do that if you think you're over designing. Maybe you can go and because you can see we have here extra capacity when it comes to the shear. So if you wish, maybe if you wish, which is right, I can go here and simply revise all my numbers, and I go to 200 mil instead of 250, and simply I'm maybe if it works and if it works in shear, then I can find here an area of steel. But let's say I'm not going to change anything. Now, again, my equation tells me you need 351 and the minimum is 500. What can you do?
Yeah, use the minimum. But the
Yes,
thing,
yeah, exactly, use the minimum. And so which means this guy will override this guy, which means going forward, I'm going to add a 500 millimeter square. And you guys know that in slab, we simply find the spacing, and how we find the spacing, this number is always constant. That is my 1 meter design strip, and this number is my area of steel, and this is for 15M. So every 15M has 200 mil. Why 15M? Because I said use 15M in your reinforcement. So we get here a 400. Luckily here, we don't have to round it, but in general, the rule is round this number to the nearest 25 mil, 1 inch. Okay. So here, our reinforcement is 15M at 400 millimeter on center. And let me just confirm. So let's go to the 3D picture and show you where is the 400. I'm asking you, this is the 400, between this and this is 400, or the 400 is between this guy and this guy. This is your 400.
that is your 400.
Number 1 or number 2?
Number 2.
Number 2. Thank you so much, guys. Those bars are the bars that we're designing right now that carry the cantilever load. The other one is a transverse reinforcement. So this one is 400. Now, you guys know that there are some code requirement that this 400 here cannot exceed the S maximum defined by 3 times thickness of the slab or 500 mil. So the maximum is 500 mil. So we're okay because the 400 is less than the 500 mil. Okay, let's go to transverse direction. So the transverse direction, we have no moment. We have 0 bending moment. We have only to add the minimum steel. We've done it already. So the minimum steel in this case is 2 per 1,000 multiplied by the area gross. Area gross of what? Let me show you what's the area gross. Okay, so the area gross, I'm going to go back to the same picture here. So where is the area gross? It is this area here, because the transverse reinforcement, it goes into this direction. Probably I will color it. So this will be the area gross, which is 250 times 1.2 meter. So 0.25 meter times 1.2 meter. Let's get 2 per 1,000 of this area. Let's do it.
But isn't that you're talking about transverse direction, sir?
Yes, it is.
Yeah, for transverse direction, it should be 1 meter width.
No. Look at this, please. I'll explain it one more time. So here is your 1 meter. Here is your 1 meter design strip, okay, which cantilevers out, supported on a wall. So this is your 1 meter design.
Okay, I got it.
This is your 1 meter design strip here. Okay. So this direction is the main direction. And what is the transverse? The transverse is this direction. And that's why we provide here, we take this area and multiply by 2 per 1,000. So 2 per 1,000, let's go back and to do it very quickly. So 2 per 1,000 multiply by the thickness, multiply the width, you get here 600, and simply 600 if we are using 15 m, then every 15 m is 200 mil. It means finally we need in this cross section we need 315 m. Okay, and something here I've never done it, but probably we should do it now. Now we never check the spacing. We never check the spacing. So let's see if we need more than 15 m. Okay. So if this guy is 1200, if this guy here is 1200 mil, okay, so what is the spacing if I add 315 m? Okay, so the 315 m here, very simple, the 1200 divided by 4, actually by 3, okay, so 3, you'll get 400. So what is 400? It will be the spacing, okay. Why? Because we're going to add here a bar, one bar here, and then another bar here, and then another bar here. And so this dimension from here to there, this will be a 400, and this will be 400, and this will be half of the spacing. This will be 200, half of the spacing, 200, and this finally will be 200. So now our spacing will be a 400 mil. Is 400 mil okay?
Yes.
Yeah, yes. Why? Because you can, the rule is here. 5 times the h, it means 1250, and or 500, which means my limit here is 500. And since I'm doing 400, it means okay. In case you get more than 500, then you have to go with this number here. So you need to space your rebar not more than 500 mil on center. Okay, dokie. Okay, now there is something I already like kind of forget about it here, but it's also important, and please take a note that do we need to do at crack control?
Yes.
I know by now, oh my God, Tahir, you're going very, very like back in time. That was beam design, one-way slab design. Do we need to do crack control check? Yes,
Yes,
we do.
we do.
Need, which is not very difficult. What you have to do is you go find the Z240 MBA, like Newton per millimeter square, and then cubic root of A times DC. There is no change. It's copy and paste from one-way slab. Okay. Now, let me show you the last part, and then we finish our class today, which is about details. So let me show you here. So the details is we have a bars in blue, and those are the main reinforcement. They are 15 m at 400 millimeter on center, and those are carrying the bending. Those they are carrying the load. The one perpendicular, which is those are almost in kind of pink, okay, or magenta. So the magenta here, those are 315 m, and those are the transverse reinforcement. My width of my strip is 1200 mil. The thickness of the footing is 250. The thickness of the wall is 200 mil. And something that probably some of you already know, we provide something called keyway. So keyway is a good way to make a good connection between the wall and the footing. And simply it's 2x material. And in this example, it's 2x6. So you place 2x6 in the concrete, and it makes kind of a U shape. And then when you bore your wall, it makes a good connection. In addition to the keyway, we also add dowels. So the dowels, typically it's 10 m at 600 millimeter on center, alternate legs. So one leg will go this way in a continuous line, and the other one will go this way and then bend the other way. This is called 10 m dowels at 500 millimeter on center, alternating legs. Now, last one, please. This is very important, very, very important. So in order for us to protect ourselves as a structure engineer, what we do, we always add this disclaimer under every single section of the building that has a soil. Every section on the structure drawing, that has soil, you will see this disclaimer. And what does disclaimer say is, it says here, native, undisturbed soil, free of organic material, with minimum allowable soil bearing capacity of 100 kBA to be field. This is wrong, huh? This is field, huh? This is not field, it's field, verified by geotechnical engineer, okay? So this will be field verified. Field verified by geotechnical engineer. Why do we do that? Because as I said, we write on our drawing a 1200 minimum depth, okay? And in our design, we assume 100 kBA for our soil capacity. Once we put this on our drawing, it is not our responsibility. They have to call the geotechnical engineer on site to come and make sure that the soil gets whatever or has whatever we assumed in our design. So you can tell this is a disclaimer, just in case if there is organic material or anything. Sometimes it is disturbed by the rain. Very, very important. Like myself, I have been in one project 10 years ago, and everything was okay. The only problem is under the rebar. So I'm going to inspect a footing under the rebar. So there was disturbance. It was raining, and there was some disturbance of the soil. So I said, okay, don't pour. Never pour concrete while before you get a geotechnical here to ensure that the soil is okay. Although I'm going for the rebar, so it's my problem is the rebar. I need to make sure that there is a 10M, 15M at 400 on center, or maybe 315M. I'm inspecting rebar, but my visual observation is on site that the soil has been disturbed. So I just noted this on my inspection report, and we stop the bore until the geotechnical makes sure that everything is okay in terms of bearing capacity. Are you following?
Yes, sir.
Okay, so you can see, what do you think about this session? Did you learn anything new today?
Nothing much new except for that the geotechnical part.
Exactly. So you can tell here, everything is old, nothing new. It is kind of one-way slab. In tomorrow's class, we will go almost along the same line. There will be one thing which is brand new, you never heard of, you never learn of, which is very special to spread footing or bad footing. Something called bunching shear. Remember this name because you will hear this name tomorrow. Bunching shear. Okay? Any questions so far? Any questions so far? Domenico has a comment. You will not see me again. You will not see me again. That is the end of Tahir for you. I'm not teaching. I teach surveying and thank you so much. I am teaching surveying and concrete design. Next semester, I'm teaching, there's no concrete for me. I'm teaching surveying plus strengths of material lab. And so that's what I'll teach next semester. Not really you guys anymore. Okay? Okay, I will finish the class now, and we'll see you guys in probably 20 minutes in surveying. Thank you.
Thank you, Tahir.
Thank you, sir.